All right, so in this video, we're going to talk about a couple different types of discontinuities. Not all of them. We're only talking about 3, but there's a bunch of different ways that something can be not continuous. So we're only going to look at 3. Oops, I'm still in green. Oh well. It's a reflection of my similarities with the Grinch. That's a topic for another time. So let's look at 3 things that we looked at before. Something like this is one type of discontinuity. In the middle, something like this is another type of discontinuity. And at the end, look at that reciprocal squared function. This is our 3rd type that we're going to look at of discontinuity. All right, 1, 2, 3. So we're going to name them, and we're going to talk about what their characteristics are. So this first type of discontinuity, let's color code. We need to use more colors in these videos. This first type of discontinuity is called a removable discontinuity. I never know whether there's supposed to be an E in there. I think they're supposed to. No, I don't even know. I'm Googling while recording a video. Is that important? All right, removable. Nope, there's no E. There's no E. Removable, just like the E is removable. It's a teaching moment. All right, so removable discontinuity. This is a specific case where the limit as x approaches a of that function exists. So notice that in these other cases, cases 2 and 3, we do not have this. All right, in these other ones, the limit doesn't exist. Because in number 2, the limit from the left is different from the right. And in the 3rd one, the limit is infinity. And remember that if the limit is infinity, technically it doesn't exist. Because infinity is not a number. So this is our first type of discontinuity, removable. It's called removable because we can fix it with a piecewise function. If we just move the circle down here, now it's continuous. The second type is called a jump discontinuity. Why? Well, because it jumps. All right, so this is a jump discontinuity. And here, the one-sided limits exist. So the limit as x approaches a from the left of the function, and the limit as x approaches a from the right of the function, these both exist, but are different. So the limit, the two-sided limit doesn't exist. A slightly different situation. And the last one is called an infinite discontinuity. We can't use green again. Yellow is kind of weird though. Oh, October's back. Infinite discontinuity. And this is, as you might expect, the limits are infinity or negative infinity or some combination. The one-sided limits are a combination of positive infinity and negative infinity. All right, so again, there are more kinds of discontinuities than just this, but these are the 3 that we're going to be naming, and these are the 3 that we are going to be talking about. She's sitting right on top of my notes. She loves paper. She will sit on paper all the time. All right, so next, I'm pretty sure we have an example. An example is something I want to talk about. October, can you just move a little bit? Just move your foot a little bit. All right, yes, example 3, classify the discontinuity. Perfect, October, you did great. Let's do that. Classify the discontinuity. Part A, let's look at this function. F of x equals x squared minus 4 over x minus 2 at x equals 2. And I'm pretty sure we did this example. Yep, that was 1C. And we showed, yes, this is a discontinuity. The question is, what kind? And the answer can be found by graphing. But I would recommend that you try to use graphing to check your answers. as opposed to getting your answers from graphing. It'll be much better for like conceptual reinforcement if you try to do it first without graphing and then look at the graph to connect the two things. So this is a rational function. Since it's rational, it can only either be this type or this type. It's either a whole or an infinite discontinuity. How do we tell whether it's a vertical asymptote or a whole? We have to factor the top. The top is x minus 2, x plus 2, and the bottom is x minus 2. Okay, if there's a shared factor in the top and the bottom, then it's a whole. So this is a removable discontinuity. And I'm not going to necessarily make you prove this unless I really specify that in the wording. But if we wanted to prove it's a removable discontinuity, we could show that the limit exists. And again, we could show that the limit exists. And again, we can find that the limit exists using methods from previous sections in chapter 2. Part B. F of x equals this piecewise function from before. Negative x squared plus 4 and 4x minus 8 when x is to the left of 3 and when x is to the right of 3. And we want to do it at this point. Well, again, we showed before that the one-sided limits existed. This was 1b. This was not 1b. This is 1a. Right? We showed that the one-sided limits existed, but they weren't the same. What type of discontinuity is that? One-sided limits exist, but aren't the same? Jump discontinuity. All right? We showed in 1a, this is jump. All capital letters. The capital letters are not important. All right, last one, and then we'll take a look at these. Part C, f of x equals x plus 2 over x plus 1. Again, another rational function. Rational functions are continuous everywhere in their domain. But x equals negative 1 is not in the domain. There's no common factors. If there were a common factor here, then maybe it'd be removable discontinuity. Maybe there'd be a whole. But there isn't. This is a vertical asymptote. Since there's a vertical asymptote, it's going to be an infinite discontinuity. All right, vertical asymptote. You could show, in fact, that the limit as x approaches negative 1 from the left, I believe, hold on, we have to do this. From the left, it'd be positive on the top and negative on the bottom. So from the left, it would be negative infinity, and it'd be positive infinity from the right. All right. So let's look at these. Let's get some graphing. I haven't really used Desmos yet. Let's graph all of these and verify. So the first one was the function y equals x squared minus 4 divided by x minus 2. And again, Desmos isn't always the best at showing the wholes. But if we look at x equals 2, hover over it, you will see the whole then. All right, so the limit exists, but the function value is not equal to the limit. Function's not even defined here. This is a removable discontinuity. This is our first problem that we just did. Second one was our piecewise function. Remember how to graph piecewise functions on Desmos? You graph one piece, and then you use squiggly brackets, braces is what they're called, to put the domain here. And then do the other piece, 4x minus 8. And again, the domain here, x greater than 3. And then you can also manually add the open and the closed circles. But either way, you can see that this is a jump discontinuity. The limit from the left exists, and in fact, it's equal to negative 5. And the limit from the right also exists. Again, you can see that open circle when you hover over it. The limit is 4, just like we did in example 1. And finally, the last function that we're looking at is this, again, another rational function, x plus 2 divided by x plus 1. This is an infinite discontinuity because it approaches negative infinity and or positive infinity, some combination of positive and negative infinities on both sides. All right. So those are the three types of discontinuities we're talking about. It's not the only types of discontinuity. And you should have enough information to get a classifying. One final sayonara from October. She's not paying attention to you guys. Have a good day. And let me know if you have questions, please.